Very good morning to all of you. Myself, Dr. Shubhadip Dasgupta, Assistant Professor in the Department of Agricultural Chemistry and Soil Science. Also, I am attached with the All India Coordinated Research Project in Soil Test Crop Response. Today, I am presenting one of my research work, that is the Smart Soil Sensing for Rapid Soil Fertility Prediction Mapping. That research was carried out from the last 3 years, and from where I have published many several good impactful papers. So for the any kind of soil testings in the field of agriculture, main problem is the soil testing and good support of the soil testing laboratory. Different government of India, they have different kinds of soil testing laboratories, but that is very limited. That is only situated in a very capital area, and for the remote area, for the remote people, they don't get that kind of support. And there is a growing concern over the food security and global climate for transforming agriculture in the way in which we used and manage our soils. So what is the existing facilities in India? Right now only there is a 980 soil testing laboratory all over the India. But their capacity to utilize the efficient time delivery soil testing support is only the 50%. So for so in this way it will take around 25 years to cover all the farm holding capacity and to reach to the poor rural farmers. So therefore existing facilities are the grossly inadequate to meet the overall need. And the major problem is the soil testing laboratory that are the mostly a static, and that are present only in the district town or the subdivisional town. And for a rural farmers, they had to go more than 50 or 100 kilometers to test their soil samples in regular basis. Therefore, they are reluctant, they are failed to get the soil testing support every year. So another constraint is the soil testing budget over is approx 130 crores to 150 crores. And also the fertilizer subsidy is growing, is increasing day by day by the Ministry of Fertilizers, and future technological backup for soil test based judicious fertilizer use is very much needed. So right now, what kind of technology is available for making soil testing robust and cost effective? And another thing is that can it provide wide coverage for soil testing program? And also, can rapid soil testing can be linked with the improved fertilizer use efficiency? That is the more challenging issue in the precision agriculture or digital agriculture transformation, particularly in the any kind of developing country like India. So from these constants and from this background, the motivation for this research is the soil test based fertilizer recommendation, which is the improved soil health and increased agriculture production and raise farm income. Laboratory based soil testing methods are mostly wet chemistry based, and that are time consuming, very tedious, and therefore it will take more time to deliver timely deliver soil testing report is very much challenging in right now. And traditional soil health management facing problem of spatial variability, challenge there is a challenges of sample collection, and also the challenge of high analytical cost. Currently in different countries they are using different kinds of new technology like pxr spectrometry or different kinds of color sensors, and also the growing of the AI and machine learning and digital deep learning kind of things. So there is a chance to use kind of image processing techniques. Also the satellite data is very much available right now for throughout the country. So these are the main future technologies which are emerging, and that can be linked with the soil fertility evaluations. So emerging proximal soil sensors, they have the advantage that they can rapidly obtain soil data and therefore can be used to predict many soil properties simultaneously. So by combining this kind of sensor platform, that is maybe remote sensing and proximal soil sensing, single sensor efficiency also can be more utilized. So there are few works which have been done by the recent times in the global point of view. That is the digital soil mapping for soil fertility parameters. So different earlier researchers, particularly in the USA or European countries, they are now using the digital soil mapping different kinds of technology, and they have the advantage. This DSM technique can provide quick measure to predict soil properties based on the predictive different kinds of predictive factors with estimates with good accuracy, as well as the good amount of uncertainty. So International Union of Soil Science IUSS has taken up the global soil map project. This is the one initiative to prepare a fine resolution digital soil map throughout the globe, and that's why this kind of initiative and digital soil mapping technique is emerging, and right now in the field of natural resource management and the field of the soil science, they are using this kind of technology. And now the PXRF, that is the portable X-ray fluorescence spectrophotometry, that is now also being used in recent times for soil fertility characterizations. So earlier defined researchers, they have been used soil PXRF as a proximal soil sensor for total soil nutrient characterizations. But the main challenge is the soil fertility estimation, because soil fertility is the very it actually counts the available form of the soil nutrients. That's why that more challenge is here, and only a few works already done so far in the field of the PX by use of the PXRF to characterize soil fertility. And these are, you can see, these are the only few works they used PXRF, and they successfully predicted different parameters, mainly the soil organic carbon, different kinds of cationic cationic micronutrients. So but in India, very limited works already only done in this field. So another interesting sensors that can be used, that is the USB microscope. USB microscope is a portable, and that can be attached with the desktop or computer, and very low cost technology and very cheap, and they can simultaneously take multiple soil fertility parameters by a good amount of model by running and they produce a multiple soil images at a time, and that images can be processed to predict different kinds of soil parameters, and only a limited work have been done so far, and this limited research work is mainly confined in the field of soil fertility, and the only parameters so far have been done, that is the soil organic carbons, and also the soil particle size, that is the soil texture, sand, silt, clay percentage determinations was done by use of the USB microscope. But the other soil fertility parameters like the soil available nitrogen or soil phosphate or kind of micronutrient, that kind of work has not been done so far. So another interesting thing is the sensor fusion. That is the when we are not taking the individual sensor data, we are actually actually accommodating the whole soil sensor data. That is the different kinds of proximal soil sensors have their different capacity, and by the sensor fusion technology and by use of the models, machine learning or deep learning, that kind of power of the predictive power can be enhanced. So individual sensor can, if suppose individual sensor have that kind of X amount of power, so when we are fusing different kinds of sensors, their power is being utilized. So on that basis, on this review, for the Indian soil analytical context, These are the main research gap that has been identified, that there is a need to explore a diverse range of environmental covariates to be incorporated in the future DSM activity. Another thing is the application of ensemble modeling rather than the individual machine learning modeling. Use of the superlearner or use of the ensemble modeling has to be tested. Another important thing that has not been done so far, a comprehensive PXRF based characterization of the soil nutrient and fertility indicator, particularly defined kinds of soil fertility parameters like sodium, like available nitrogen, like potassium, calcium, and mainly the different micronutrient like zinc, like iron, like boron, that is actually deficient in different parts of the country. And if this kind of sensor technology can be used to identify the pocket locations by use of the machine learning or deep learning, so that can be tested. So on that basis of research gap, these are the objectives that have been fixed. That is that to create a high resolution digital maps at the regional level depicting spatial prediction of the essential soil micronutrient using remote sensing data, digital elevation model, and the climate database as covariates. Also, second objective is that to evaluate the potentiality of the PXRF for rapid soil fertility prediction and fertilizer recommendation. Third one is the evaluation of the potentiality of the a low cost, very cheap, and very easy to use USB microscope as a image sensor for image based processing for rapid multi-nutrient assessment and soil fertility characterizations. So these are the interconnection between the different objectives. So all objectives are towards for a additional support for the traditional soil testing and mapping, and also this kind of these four objective can be a supplemental for rapid demand for the regular and spatio-temporal context soil testing and their judicious fertilizer recommendations. So this kind of proximal soil sensing and the remote sensing based data set can be used as a covariate, as well as this kind of data set can be used independently to predict different soil fertility parameters for judicious fertilizer recommendation to the every single householding family or the farmers. So for the first objective, that is, these are the materials method which have been followed, and for that in the West Bengal, South West Bengal states, mainly the 9 districts were identified, were chosen, and in these 9 districts, a stratified random samplings were chosen for collecting more than 1700 soil samples, and that soil samples represent the 0 to 30 centimeter depth of soil samples, and 4 different agroclimatic zones, that is the Gangetic alluvial, coastal saline, Vindhyachal alluvial, and the red alluvial zones were selected, and from where the soil samples have been done. So this is at the overall workflow. So 1750 soil samples first collected. Parallelly, the multi-source environmental data were also extracted from the open source satellite data, that is the Landsat 8 data, and SRTM DEM data, digital elevation model were extracted, and parallelly from the same locations climate data were extracted. All data were extracted in the 1:30 meter resolutions, and after the atmospheric corrections from the Landsat 8 remote sensing data, 17 number of different kinds of indices, that are the covariates, and that covariates are selected that are very much related to the soil, water, and the vegetations. Similarly, 20 terrain covariates were identified and extracted. Similarly, 15 climate covariates were selected, and parallelly laboratories from the soil samples laboratory analysis were done, and finally the models were built to predict different kinds of micronutrients like zinc, copper, iron, manganese in their available form, and we have developed the one kind of interrelationship between the whatever the available micronutrients are present in the soils along with their interrelationship with the crop response or the bioavailability in the along with the whatever the presence of that kind of micronutrient in the crop body. So that interrelationship have been built, and by using that interrelationship we have mapped also not only the soil map, rated soil micronutrient map, but also we have mapped the biofortification potential of the entire zone. Finally, we have produced the good quality digital soil map. Parallelly, we also predicted the biofortification potential zone. So these are the environmental covariates. You can see these are the different kinds of environmental covariates are extracted for the remote sensing data. For the terrain covariates, different kinds of terrain covariates. Out of total 54 covariates are extracted initially among from the and that represent terrain, climate, vegetation, water, soil, and our hypothesis was that this kind of covariates will ultimately influence the overall micronutrient availability in the soil. So these are the remote sensing covariates are used. So Landsat 8 data were extracted, and from the Landsat 8 data also different kinds of indices. That indices were actually earlier used by different researchers for vegetation study. That's why these kind of indices were chosen for this work. Finally, all the covariates map, all the defined kinds of 20 covariates map were extracted in 1:30 resolutions. So these are the one example of these are the defined kinds of example of that kind of covariates. That are the raster map. These are the annual precipitation, that is the climate data, and that is the channel network distance. You can see this is the terrain data, NDVI, that is the remote sensing data, and soil acidity, this is the soil analytical data. All different kinds of data were extracted that were in the raster format, and finally all covariates data were extracted, and also all these covariates are utilized for the machine learning model. So these are the 14 machine learning models were used for this work. So purpose is to test their individual results of this individual extract. Also, there the interrelationship between these machine learning models along with the whatever the good results they are giving. Parallelly, we have tested the ensemble models in between them. So this is the materials method for the another objective 2, 3 and 4. So here you can see the for this image processing based work and also the PXRF based work, all both are the proximal soil sensors, and for that the 560 soil samples were collected throughout the different zone, different strata of the West Bengal. So our purpose is to extract all the soil variability from throughout the states. That's why the whole state have been chosen from where from the different strata, different soil samples was collected, and these are the overall soil description from where soil samples have been collected. So you can, after the soil sample collections and the processing, these are the soil parameters have been tested for the before the machine learning model. So all the soil fertility parameters that actually followed by the regular government soil testing laboratory, that all parameters have been tested in our laboratory, and the reference was the whatever the regular soil testing laboratory which have been followed in recent times, that same method was followed for this research work. So for the second objective, this is at the workflow. So here we have, after the soil sample collection and in the laboratory, we have scanned by the, these are the PXRF proximal sensor, and this PXRF provide the rapid scan, that is the 90-second scan. By a single scan, we can get a lot of data, lot of informations, and we are also using the different kinds of auxiliary variables. These are the auxiliary variables like the agroclimatic region, parent material, soil order, productivity potential. All the auxiliary variables along with this kind of PXRF data, we have developed the model, and for model development we have used the random forest, support vector and SMLR, and finally average, their average model were done, model was also checked. So these are the USB microscope based work. This is the objective 3, and for this the same soil samples have been taken, soil sample image have been taken by use of the low cost, by developing a low cost setup. These are the image setup by using the one single laptop and the one single USB microscope. And the you can see the every soil samples, they produce a very good amount of information, that is the color information, and that color informations were extracted by the image processing techniques, and that information was used for the final machine learning model. You can see the image processing, which was image processing was done, and from the image processing we can get the sufficient amount of the image extracted values, and that numeric values were used for the models development. So these are the first now the results. We can see all the soil samples, they produce a good amount of the variability. So that means the all tested all the tested parameters show sufficient amount of variability, and this represent the all the soil samples capture the overall variability, which actually represent the throughout the state the variability. So for the first objective, out of 54 covariates, we have extracted 20 top 20 covariates and top 20 covariates for a individual predictor. So for zinc, copper, iron, manganese, we have isolated the top 20 covariates. So these are the model results. Here 14 machine learning model were tested. Also their ensemble models are also tested along with this individual base learner. We can see that the ensemble result is delivering a very good amount of RMSE, good amount compared to the individual machine learning model. Among the individual machine learning model, the forest based algorithm, that is the random forest or quantile regression random forest RPART, they are providing good result for all the predictors, that is the zinc, copper, iron, manganese, and in all cases ensemble models are found to be superior. Similarly, these are the ensemble model results. We can see a very good amount, a sufficient amount of RMSE were established by this kind of ensemble model, and this ensemble model can predict good amount of RMSE and the MAP for the zinc, copper, iron, manganese. So these are the VI variable importance plot for individual model and the individual for the different kinds of micronutrient predictions. Among them, we can see the climatic covariates which found to be superior than remote sensing covariate than terrain covariates for predicting the available soil micronutrient. So these are the correlation matrix between them. So we can see the PDP partial dependence plot, and for the partial from the this kind of partial dependence plot, we can identify that the what kind of correlation or what kind of interrelations was there between the different kinds of covariates, remote sensing covariates, along with the overall the predicted value. So finally, micronutrient predicted map was generated for from the collected soil samples. These are the whole south West Bengal, southern part of the West Bengal from where soil samples are collected, and with good accuracy, these experiments gave the very good amount of digital soil map. So these are the prediction limit range, objective 1. So finally, by use of the interrelationship between the crop and soil, finally this kind of actually the biofortification potential map were generated individual block wise, pocket wise. By this map, anyone can say what level of micronutrient deficiency were there. So these are the overall, we can see the iron deficiency were there very much. So these are the objective 2 result, and this is the descriptive statistics. We can see there is a good amount of variability in between them. So these are the PCA results. We can see this kind of PXRF, PXRF as a proximal soil sensor can provide a good amount of variability, and they can capture the variability actually. So these are the prediction model results when we are using the PXRF plus and as a single, also the PXRF plus A1, that is the auxiliary variable, plus PXRF plus A1 plus A2. When we are using the PXRF plus A1 plus A2, both are the auxiliary variable, different types of auxiliary variable. When we are using PXRF as a proximal sensor plus different types of auxiliary variables, they are producing very good amount of accuracy for all kind of prediction model. Here random forest, support vector and SMLR, three kind of prediction model were used. Among them, random forest was found to be superior for most of cases. So these are the RPD value. Same RPD, in the case of RPD, residual prediction deviation, we are getting the similar kind of results. So these are the RPIQ value. So finally, these are the predicted plot, and we can observe versus predicted for the defined types of soil fertilizer. From this predicted plot, we can identify that by use of the PXRF and the auxiliary variable, we can get a very good amount of prediction accuracy. So PXRF can be used. So these are the all variable importance plot. So these are the overall the conceptual framework which can be used. So these are the objective 2 summary overall. So for the R square and RMSE, when we are using the image features, our objective 3 is the use of the USB microscope. When we are using USB microscope, also we are getting very good amount of R square and RMSE. And when we are using the image features that is found by the USB microscope and the PXRF, we are getting a very good amount of R square and very low amount of RMSE. So these are the sensor fusion, that is the sensor fusion. By the sensor fusion, that is the PXRF and also the image features, we can get a very good amount of accuracy for most available micronutrients. So when we are testing the zone wise holdout validation test, also it is found to be superior in most of different kinds of zones. So final conclusion is that the ensemble model is better than the individual base learner, and micronutrient maps can identify areas where crop variety with the biofortification potential. So therefore regional scale micronutrient basements can be developed. So another conclusion from this work is that the agroclimatic zone, physiographic and routine soil test parameter can be used as an auxiliary variable along with the PXRF for different kinds of soil fertility predictions. And combined PXRF and the different kinds of auxiliary variable, soil fertility test classification has potential for future site-specific nutrient management. So these are the major achievements from this kind of research work from my research group. We have developed soil image processing based soil fertility sensor, regional soil micronutrient management strategy, established PXRF based multiple soil fertility evaluation, a developed framework for PXRF plus auxiliary soil properties, developed website for use of soil testing personnel for on-site fertilizer recommendations, identified Nix Pro color sensor as a potential option, and finally also the developed digital soil microgrid from the South and West Bengal. So these are the important research paper for this kind of research work for the last few years. So very good impact factor journal publications have been done from this kind of research work. These are the my different kinds of also the different kinds of research for the last few years by myself and my students. So also the different kinds of others from not only the soil sensing technology, also other kind of research work is also going on. So these are the book chapters which I have published. So thank you everyone.